you're in the WebAssembly talk. And the whole focus of what I'm going to share over the next 45 minutes is really the answer to the question of what if I told you that you could run code in a browser, and this is any modern web browser, at near native speeds. So we're talking speeds close to what an installed desktop application would actually run without using any type of plugin. And even more powerfully, using the programming language of your choice. That's what we're going to explore. And I want to kick off with just an example. Is anyone familiar with Unreal Engine, out of curiosity? So it's a 3D engine that was ported to WebAssembly. This is WebAssembly running in the browser without a plugin. And what I'm going to do is just zoom into this pool. You can see 3D water effects, and these fish are swimming around, and I can interact with this, use my mouse, and actually draw them to drag around. So that fluid experience is the full Unreal Engine running in the browser. I'm going to close that out and take a step back. This is WebAssembly, talking about browser as the OS. I'll spend about 2 seconds on my bio. I'm a cloud advocate at Microsoft. If you're curious what a cloud advocate is, feel free to stop me afterwards. I'll be happy to explain it. I've been developing for a really long time. So non-professionally for over 30 years, professionally for 25 years. So I've seen a thing or two in my day. I like to run. I put that in quotes because if anyone actually saw me trying to run, they'd realize it's a slow jog, but it keeps me fit. I try to follow a 100% plant-based diet, but you never know what happens in the kitchen, so I drop the percentage just a little bit. And I love shooting pool whenever possible. Everyone will get access to this deck. The contact information in the lower left is how you can reach out to me. Suggestions, feedback, questions, happy to respond. That is a real email address. It does not have a forward rule that just sends everything into the trash can, so I will respond to you. I want to start, what's that? Sure thing. And you will get access to this afterwards too, so all these links will be available for you. So I want to start with this premise. This is perfectly valid JavaScript code, and what it's doing is a very inefficient brute force attack to compute primes. And it's going through and doing division and figuring out is this number a prime, and it returns the highest number prime it finds in that range. Now if we take a look at an actual code example, the primes example looks like this. I actually increased the number of primes up to 80,000 just to make it interesting. And then this little exports here allows me to wrap it in a node process. So this is my node wrapper. It's pretty straightforward. What I'm doing is I'm including the primes, starting a timer, running it, getting the result, ending the timer, and showing you the result. So if we run this, I'm just going to drop to command line here, and I'm going to run node primes.js. This is going to pull in that module, go through that brute force with JavaScript, and hopefully it'll compute the correct prime. It'll return back to us, and you can see it took about 8.8 seconds. So we'll keep that in mind for JavaScript. Now let's take a look at the precursor to WebAssembly. Is anyone familiar with Asm.js? Out of curiosity, so Asm.js came out about 2014. And it's an interesting concept. The idea was take JavaScript and create a subset of JavaScript, so constrain the language, if you will, and do things like don't allow for loops. Everything has to be a while one loop, and I'll show what that looks like in a second. But the idea is with this constrained subset, it can now be a target for typed languages. And there's a little bit of infrastructure around it to create a memory heap so that you can access memory, but it's a stack-based virtual machine. And because of this target, you're able to actually take code and compile it to JavaScript. And then modern browsers that are aware of Asm.js are able to optimize that code. Because of that subset, they can have a highly efficient way of optimizing it towards native code. And it'll make more sense in a second. So the tool chain that this started out with was taking our favorite language, right? C and C++. Dating myself, this is how I got started after mainframe programming. Clang is a tool that generates code from C and C++. If you're not familiar with LLVM, this is a tool chain that makes it possible to build compilers that target multiple platforms. So if you're part of this tool chain, you have access to a suite of resources that makes it easier to target platforms. And then on top of that, this module called Emscripten came out. And what Emscripten does is it takes the output of that C code and creates ASM.js code. Sounds like a lot, but I want to start with this simple example. This is the same primes computation written in C. The big difference between C and JavaScript is JavaScript has a number type. And if you're familiar with JavaScript, it's basically a floating point number type. And floating point math has a lot of overhead associated with it. It's not that efficient. In C, I can declare an integer type. And integer math is far more efficient. So taking that C code, what I can do is use the Emscripten toolchain and start with something like this, which is just that compute primes. Notice I call it compute primes ASM. And this is written in C, and I can compile it and get something that looks like this, which makes a lot of sense, and everyone's already debugging and troubleshooting the code. It's actually a lot bigger than my primes.js, but it's doing a lot of housekeeping. For example, in C, you can work with standard input and standard output. There's no concept of that in JavaScript, so it's basically marshalling those standard input and output, mapping memory, etc. This is a more practical look of the expanded code. I'm going to dive into this in a little more detail, but what I want to show you is I've got this same wrapper around primes.asm.js, same timer, get the result, compute it, and I just want to run this for a second. So let's do primes.asm.js. So this is going to do the same thing. It's a node module. It's going to pull in the ASM. It's going to run through, compute the prime, return the highest number prime. And you can see we shaved off about 1.2 seconds. So that's over 10% performance. And if you scale that out to more complex algorithms, and the entire reason it was able to do this is because it was using integer math instead of floating point math for that operation. This is a very simple example. This is the code for all practical purposes that was generated. And if you take a look at it, it looks a little confusing, weird variable names, etc. But there's some interesting conventions here. For example, doing an exclusive OR with 0 in regular JavaScript, if the engine's not ASM aware, this is just going to remove the fractional component. So this is perfectly valid JavaScript. For an ASM aware engine, though, it knows that this has to be an integer, and so it can marshal and do integer math with that instead of floating point operations. We've got an example here of the while one loop. Everything's a while one with a break. And again, by having just that one type of loop, it allows for compiler optimizations. This is an example of an operation that's been coerced into an integer, and this is a decrement. So it's actually moving the variable, creating a new variable that's the result of adding -1, forcing it to an integer, passing it back. Seems inefficient, but if you understand compilers, it actually creates a pipeline that is highly efficient for compilers. That's interesting. These are some times in Chrome that shows how it consistently runs faster. But what's more interesting is building on top of this in 2017, the WebAssembly specification came out. So this is still pretty brand new. It's only a couple years old. But what's important to note is that all of the major browsers, the current versions of all major browsers, support WebAssembly out of the box, nothing special to do. And this includes the browsers on your phone. So every example I show you today can just as easily run on your phone as it does on a desktop-based browser. So what WebAssembly does is creates this notion of a stack-based virtual machine with its own bytecode language, its own assembly language. It's a WebAssembly. This is the same algorithm to compute primes in WebAssembly. I don't expect you to understand, troubleshoot, or debug, just showing you conceptually how that's output. Now, WASM has a few advantages over ASM.js. First off, WASM's compiled, so there's no interpreting the script. For example, you can write ASM.js and say it's ASM.js, but then you can cheat and not use an exclusive OR 0, etc., and use a for loop, and it's invalid. So it has to parse that and make sure it's valid. Then it has to do ahead of time compilation. Here we're in a bytecode format. In fact, the primes operation, when I compile it to WASM, is just 112 bytes, as opposed to something like 11,000 kilobytes for the compressed JavaScript that you saw. Finally, it has its own instruction set. So it's not constrained by a subset of the JavaScript language. It can be a full-blown set of instructions as a target for a compiler, but it still runs within the constraints of the web sandbox. So I want to show you kind of what that performance looks like in this example. And so what I did is I have pretty much the exact same C program, only this time I've renamed it to Compute Primes WASM instead of Compute Primes ASM. Now when I compile it, what I'll get is I'll get this primes.wasm.js. That's about 11,000 bytes. This is JavaScript loader code. Right now, WASM doesn't inject directly into the browser. You need to wrap it in a fetch and kind of wire it up. So there's some boilerplate that's generated for you automatically by the Emscripten toolchain. This is the actual WASM file here, this wasm.wasm, 112 bytes, so very streamlined. So what I did for this example is I created a little web page, and all it does is it loads the primes.js, the primes.asm, and the primes.wasm, wires up some buttons, and the main function is pretty much the same for each one. Computes the prime, starts the timer, gets the result, ends the timer. So it's feeding it in, but it's going to use one of the different engines. So what I can do is launch a simple little web server. Actually, I just destroyed my code here. So I can launch a little web server in this directory. We can come over to our web page and we can navigate to localhost 8080 primes.html, and we see our buttons. I'm going to go ahead and open up my console. And don't worry about the errors. That's just because I have the module exports and I'm doing it in the browser and not in Node, so it sort of ignores that error. If I do it in JavaScript, we can see in the console it's computing that prime. It's going to spin a little while, get the method. This should run a little bit faster than Node. It actually ran slower, 9.2 seconds. Now let's go ahead and do the same thing with WASM. So I'm going to click on the WASM button. Says it's computing the prime, spinning around, and 6.7 seconds. So you can see substantial improvement right there inside of the browser for that. And all of this code, by the way, will be available for you to pull down and troubleshoot yourself. So I talked about it being a stack-based virtual machine. It does have memory. If you write a C program, you're going to have memory manipulation. If you use something like Go or C#, you have managed memory. So you need memory. So WASM exposes memory in heaps. There's actually byte-aligned memory. So I have 8-bit, 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 8-bit. But based on the type of variable I'm dealing with, I may take up a different set of bytes. For example, a 32-bit integer is going to take up 4 bytes. So every 4 bytes is an integer in that. So to make it easy to access it, it exposes these different heaps that are all looking at the same memory addresses just in different ways based on the type of memory you're indexing. These correlate to new arrays that have been introduced into JavaScript that are the ways that you actually do get typed integers, typed numeric values in JavaScript is through these typed arrays. And you've got integers, you've got float, and you've got unsigned variations on all of that. So to show what that looks like, it's a little interesting. If I start on my C code side and I create a buffer, that buffer is automatically going to be allocated for me in WebAssembly, and it's going to be available to JavaScript. If I want to allocate a buffer on the JavaScript side and pass it in, I have to go back to my old C days and actually allocate that memory. And I have to allocate the right amount of memory because there's just one method, malloc, memory allocation. So if I'm allocating memory for 2 32-bit integers, I actually need, it's 4 bytes per integer, so I actually need 8 bytes total allocated for that. Then I have a buffer that I can set some values and pass it in. So to show what that looks like, I created something called the chaos game. I'm gonna pop out of here. No, don't save the changes, not coding live. So this is C code. And it's a pretty old algorithm that's been around since the 80s. It was one of the first chaos type fractals I worked with. basically the way the chaos game works is you start with a bunch of numbers. This is the tree initialization. This is the fern initialization. You'll see what it looks like in a second. But these numbers represent transformations. So you can scale, rotate, and move a point. And you'll have multiple transformations. And the way the chaos game works is you start with an arbitrary point, you roll the dice, pick a transformation, and transform the point. Then you roll the dice again, pick another transformation, transform that point. So if you look at the way the code works, when we come in here to render the tree, it's coming through, it's initializing the model. It's basically getting a random number, picking a transformation. This is code to apply the transformation, and it's plotting the point. And that's it. So the way that this is set up is on the JavaScript side, I'm going to initialize a buffer and send it in. I only do that in the code example so you see what that looks like. I don't have to do it. I could create the buffer in C. In that buffer, I draw a set of grid lines just so that you can see, yes, indeed, what we build in JavaScript is passed in. Then this code plays the chaos game, and it actually runs through 100,000 iterations. If you look at the code here, it's 0 through 99,999. So it applies all those points, passes the buffer back. So I have some JavaScript code that interacts with the WASM. And it does a few things. It's doing some interesting math to map into the pointer heap and come back and forth, and I'll talk about that in a second. But if we look at this, this is where I'm creating an array that represents my buffer, my grid. This is some code that's just basically bisecting the grid. It's creating a line down the middle and a line across the side. And then it allocates the memory for that, passes it in to WebAssembly. And there's a reason why I'm showing you the pain of this, because it does get easier when we go to other languages. I just want to preface with that. So I'm doing some manual memory operations. I'm calling the render tree function that does all the iterations. It passes me back a pointer to the buffer it created. It's actually a different buffer than the one I pass in. You don't have sharing. It actually copies it into WebAssembly and then gives you the pointer back out. So there's some nuances like this is the reason I created this project and some code around it to explain. But I get that offset out of it, and then I can basically just map that offset into a buffer that I throw into an image data object. Anyone familiar with image data if you've done canvas manipulations? This is just a buffer of RGBA values that I can map onto a 2D canvas and render it. So it's very abstract right now. It's like, what the heck have I been talking about? All I can tell you is that when I compile it, I get this, let's go into the web, actually. When I compile it, I get this WASM file that's 21,000 bytes in size, so give or take 21 kilobytes. And let's go ahead and run it and see what this thing looks like, because we needed a reward for all of the talking that I've been doing. So we're going to pull this open and need to refresh because it was cached. Okay, so we've got a tree, we've got a fern, triangle, maze, snowflake curve. And then what I did to make things interesting is I have this distort function, and this is every animation frame. It's now randomizing those seed values so the transformations are changing on the fly. So you can see the grid lines that were passed in. So indeed, those were successfully passed back and forth. And this is an interesting set of functions here, because as I'm manipulating the array in real time, I'm exposing those values, because you might go off and let this run for a while and come back and find out there's the most amazing fractal anyone's ever discovered, and you need those values to do it. But it also serves another purpose, and that is, let me go ahead and close this server down. It allows me to show what some of those memory interactions look like, because it's a little bit interesting. So I have these variables A, B, C, D, E, and F, and I've got this load values routine that just gives me pointers to the beginning of each of those arrays. So these are arrays of floats. So I have an array of pointers to arrays of floats. This is getting back into the low-level, non-managed language fun that we have. So for each one of these, basically pointers to memory are unsigned 32-bit integers. So that's why I go into the unsigned 32 heap to get the offset. So this is, each time I come through this, I'm getting the offset to the A array, the B array, the C array, like that. Within that, I've got 4 different values. So I want to show those values. Those values are floats, so I go into the float 32 heap to get the float values, and then I successfully pull it out. So it's a fun, or some people might call it painful process, but you can pass memory back and forth between JavaScript. Now, WebAssembly will not talk directly to the DOM. It will not talk directly to Canvas, etc. You have to marshal it in and out of JavaScript. It adheres to the security sandbox in your browser. So we do the heavy computation inside of WebAssembly, and then we use the JavaScript to actually map it. But you can see from the animation that even 100,000 iterations of complex transforms performs quite well. The 21K is the size that came out of this. Just because WebAssembly is new doesn't mean you can't have a DevOps workflow around it. Every example I'm showing you, I don't have time to dig into the details, but is fully automated. So when I make changes, it's going to build that. In some cases, like here, I'm using a Docker container so that I don't have to set up the full mscripted environment to do that. And then I'm deploying it to a static website, and that stands it up automatically. So it's totally modern pipeline and workflow. Do I have any Go developers, any Gophers in the house? Cool, we'll go through this really quickly then because it'll make no sense whatsoever. So Go is a language, came out of Google. It's a really pleasant language to work with. It's designed to make concurrent coding easy, has garbage collection, structural typing, deals with concurrency, and there's a runtime associated with Go. So unlike C, where you're just compiling bytecode that talks to the host platform, there's a runtime because Go has managed memory. So there needs to be some overhead of managing the code. In 2018, Go embraced WebAssembly. And what's interesting is when you compile a Go app, you can target Windows, you can target Linux, you can say it's a 32-bit platform, a 64-bit platform, an ARM platform. If you want to do WASM, you target JavaScript as the operating system, interesting, and the architecture is WASM. And then it gives you some of these methods that allow you to interact between the JavaScript and the WebAssembly. So what I did was I took an old effect, again showing my age from my Commodore 64 days. We used to like to show these plasma effects, and I went ahead and implemented it in Go. So that is Rust, we want Go. So this is what it looks like. It's giving me a squiggly line, but that's fine. This is my JavaScript interop. And I'm going to just go through this at a really high level. So this is a main loop. And this JS funcof says take this Go function and make it a function that, no, don't scan for viruses. Make it a function that we can call from JavaScript. So what are we going to do? We're going to update the plasma, get a buffer. This window call is going to call a JavaScript algorithm. Request animation frame is how I'm saying every frame update it, so run at the behest of the host machine instead of using a set interval. And I call it out. So the update plasma itself is a lot of crazy code that's just basically moving a buffer palette around based on a sign computation. For efficiency, we compute the sign table up front, so we're not computing signs on the fly. And then we have a palette for our colors. And when we start out, we get the window object, get the document object. I'm creating the canvas from within Go. I'm setting the height, the width, appending the child, and doing that. I also have this plasma.js, which is a wrapper around it. So when Go calls plasma render, it's getting the buffer, mapping it to image data, putting it on the canvas. Pretty straightforward. This is actually loading the WASM. This is the wrapper around it. It's going to fetch it and call it. So not too much complex code there. And I literally just take that Go app, say target JavaScript and WebAssembly, and then what do I get? Well, this will be a little interesting, I think. Plasma.wasm is 2,151,000 bytes. Pretty large compared to the last example. Still runs quite well. Let me go ahead and launch my HTTP server. And let's pop over and force a refresh. So there's our plasma running in the browser. But we definitely had a little bit more overhead, I think, in size than we probably would have preferred for that. The reason why you get that overhead is because the entire Go runtime has to be injected into WebAssembly. So Go code won't run on its own. So the minimal Go package has to have the Go runtime, and then your Go code is on top of that. So that results in a 2 megabyte file when I do my automated builds. Any Rust developers? All right, we don't just have Rust developers, we have enthusiastic developers. In fact, Stack Overflow says it's one of the most loved languages for those who do partake in Rust. So if you don't love the language you're working on, try a little Rust, maybe. Rust is an amazing language. It's like C in that it'll compile to direct code for the platform. There's no runtime, but it's designed to make coding safe. It makes it very difficult for you to accidentally have multiple threads that collide with each other, that mutate code. There's a concept of ownership that avoids manipulation of values unless you have an explicit opt-in. And I'm super oversimplifying it, but it's a very interesting and amazing language. What's really cool about Rust is they came out of the gate completely embracing both arms WebAssembly, and not only built a way to generate WebAssembly code, they built a bunch of scaffolding around it that makes it much easier for you to interoperate with Rust values in the browser, as well as create projects. So to compare apples to, like Macintosh apples to, what's your favorite type of apple? I don't even know. What's that? Pink Lady. So to Pink Lady apples, I wrote the Plasma in Rust too, right? So side-by-side comparison. Let's see what that looks like, shall we? Yes. Okay, we're excited. Here we go. So here's the Rust. The code's going to look very familiar. Even if you don't know Rust, it should be straightforward. I've got the idea of a color. I've got this Plasma object that is going to contain my buffer and all the values that I'm going to render. But there's this, you keep seeing this hashtag WASM-bindgen. This is a really cool feature in Rust. I told you, you saw the complex math and the hoops I had to jump through just to map memory back and forth from JavaScript. Rust will just do it for me. So in other words, instead of me having to do the math and use this heap or that heap, I just tag this WASM-bindgen, and Rust says, oh, I'm going to spin up a JavaScript object that you can just talk to Plasma and not worry about the interop. So it makes my life super, super easy. I'll show you what that looks like. The code is very, very similar. We've got code to make basically a new object of this. It's still going to initialize a sign table. This tick function is just moving the sign values around. We're creating the palette the exact same way. So a small bit of code. The interesting thing about this code, you didn't know it would get interesting, did you? Is that if we look at this, I've got this, I think it's my package directory. So this is my Rust WASM, 67,000 bytes compared to 2 megabytes that I did in the Go code. But I actually have 2 projects here, which is the other cool thing. I've got a Rust package project that lets me write the Rust code and use something called WASMPack that just says generate the WASM. And then I've got a Node project that I can use Webpack to interop between WASM and Node to make my life even easier. And what I mean by that is if we take a look at the code in this directory, so this is my HTML file. I'm basically setting up a style. This is basically the extent of my CSS expertise right here, and I'm pretty sure I copy and pasted that. I've got a bootstrapper and I've got a canvas. That's what this does. If we look at my bootstrapper, actually there's a generated bootstrapper and there's a, where am I going? This is my bootstrapper. I'm importing index.js, which this would not run directly in the browser. But look at this. I'm importing the Plasma. I'm importing the memory of the Plasma. So that's an opt-in if I need to interact with memory. I'm creating a new object. I'm doing a render loop, just calling tick. I'm getting the buffer. Notice that there's no weird math or going to a different array. I'm just passing it straight into the array that the image data needs, and I'm done because Rust did all that interop for me. And then when I want to run this, I just do an npm, npm start. And we load up an npm server, and this is going to be so anticlimactic because I talked this up so much. But if we go to our local host, first thing you're going to see is my cached Go. Then I'm going to refresh it, wait for it. There we go. There's the Rust Plasma. So there you have that. And again, when I build this Rust, I get 65 kilobyte file size, so much more streamlined. So I'm going to stop here and vote that for optimized WASM sizes and ease of development, Rust is a clear winner right now for WebAssembly. And that's a Microsoft employee about to talk about C# now, so for what it's worth. Because one of the cool things that happened is immediately after WebAssembly was released, a team was able to take the .NET runtime and port that to run on top of WebAssembly. Do I have any .NET developers? Few more hands there, great. So .NET on WebAssembly. Now .NET on WebAssembly by itself, not too effective because it just runs things. You need to be able to interact with that environment. And so the first question is, why would we even bring .NET into the browser? And there's a few arguments for this, definitely using the languages of the choice. I talked to C# developers around the world, and for some reason they just don't love JavaScript like those of us JavaScript developers do. And it's just a thing, they would rather use C#. There's a huge ecosystem out there. It's already been optimized for performance. It's been out almost as long as I've been a professional developer. It's a full stack, tools, stable, and mature. But .NET by itself isn't good enough, so there's a library on top of .NET called Blazor. What Blazor does is it extends .NET to make it effective in the browser. It allows you to develop web application experiences. Because it's WebAssembly, there's no plugin, there's no code transpilation. It's going to work in all the modern browsers. Do I have any ASP.NET MVC developers out of curiosity? Are you using Razor templates? Yep, so Razor templates is a templating architecture that we use on server side. The server renders the template, sends it to the browser's happy. What Blazor does is take that exact same template style and allows you to create single page applications, only these will be rendered in the browser through WebAssembly. So you get that advantage of scaling out the distribution of the rendering engine. Same reason why we like Angular, React, and Vue is because we take a small data payload, transform it in the browser, provide that experience to the end user. So what we have is WebAssembly with .NET on top of that, Blazor on top of that. They finally got a cool logo. Don't at me. And but Blazor provides all of these services on top of that. So I'm not going to give Blazor an award for the most streamlined assemblies because we do have to deploy the entire .NET runtime, just like Go has to deploy the Go runtime. But for ease of use and developer experience, there's something to be said for how this works. So I just want to show you an example. And unlike the other languages where I install special tool packs and pull down templates and then get started and tweak and do this, to get started with Blazor, I do file new project, pick a Blazor project, and I'm ready to run it and it's good to go. So the tooling is very straightforward. What I've done here is I said, I want to create an example that is going to allow me to build my own blog engine because there's just not enough blog engines. I mean, there's Hugo, there's Gatsby, there's Jenkins, we need more. And I want to be able to preview Markdown in the browser. So what's really neat about this is because we have the full .NET runtime running in the browser, we don't compile special DLLs for Blazor. Blazor will run as is existing class libraries or DLLs. So what I was able to do was I was able to import a package called MarkDig. That's the right here. And MarkDig is just a class library that allows you to convert Markdown to HTML and provide some tools. The author of this, I'm very confident, wrote this as a server-side class library to be included in .NET applications and had no notions of this ever running in the browser. However, we went ahead and included it in this client-side application, and really this code is about as simple as we can get. I've got a A little bit of HTML markup that you see here. I've got a text area. This is where I write my award-winning blog post. I've got a click, and this is how I do interop, by the way, between HTML and Blazor code. This @convert means run this convert function in code. This is C# code, and it's going to automatically wire into the event, call into the C# code. What I'm doing is using MarkDig to take my source text, convert it to HTML. Now, there's a longer version of this where I just focus on Blazor, where I do it the first time, and it's a little bit boring because it's escaped HTML. Blazor happens to follow the rules and wants your HTML to be safe, so it doesn't just take anything someone pastes into a text box and renders that, because that can come with issues. Angular, React, all of these have provisions for that. So what I decided to do is use a little bit of a trick, and here I'm calling into JavaScript. So there's interoperability between C# and JavaScript with what I'm doing. And what I did was exploited an interesting trick that I was not clever enough to figure out on my own. But basically, I create a text area on the fly. I set the inner HTML to the escaped markdown that I get. So this is an escaped. And it turns out that the value of that text area will be HTML that can actually be rendered. So I'm calling out to JavaScript, creating a text area, moving escape code in, getting the actual unescaped HTML out. And then in Blazor, if we come back to this page, I've got this element ref of target, and you can see I have this paragraph, ref equals target. And basically, if I did the preview, you'd see the escaped HTML. This gives me a reference that I can pass around. So here I'm passing it into the JavaScript code. So these are reusable components. Every component that I make in Blazor is automatically reusable and drop-in. So like if you see this counter component here, this counter, I can actually just drop in a tag called counter in any of my pages. Actually makes more sense if I look at this shared. So this has a markdown, a nav menu, a survey prompt. All of these are components that I can repeat. So by using this syntax of doing the reference, I don't have to like try to navigate the DOM and figure out which copy of the component I'm dealing with. It gives me that exact reference. So I've done a lot of talking, as I tend to do. Let's go ahead and run this and let it build it. And I want to show you a couple things in the build for this. So now it's loading. Okay, we've got our Hello World app. So before I do anything interesting here, I want to open up my DevTools, go into the network, and just load it again and show you a little bit about what's going on here. So here we're getting CSS, we're getting this WebAssembly file here. It's kind of a bootstrapper. And then as we come down, we get mono.wasm. This is the .NET framework written on WASM. And then everything after that is all DLLs loaded directly in the browser. Now, part of the effort that Microsoft is taking before Blazor becomes full release, it's in preview right now, is to do things like tree shaking and optimization so that the DLLs that are served only have the code that's actually being used. Because I could pull in a library that's 5 gigabytes and I might use 2 megabytes of code, and that would be inefficient. There's also a limited debug experience that they're working to improve upon as well. Is that a question?
Yeah. Before you post the tools, what does the elements look like? Are those is it still in the DOM tree, or is everything kind of like in a box?
Oh, so you want me to do F12 elements, and then let's look at this. So if we look at that, it's an actual H1 tag, it's an actual text area tag, it's an actual button tag. So Blazor's come back and wired it up. Now this one's gotten this extra attribute on it so it can identify it if there's multiple copies, but it is creating actual HTML tags, and there are well-documented ways of augmenting and using existing JavaScript libraries. So I'm gonna go ahead and say header. We all know Markdown by now, right? Subheader. Let's do a unordered list, 1, 2. And no talk would be complete without a shameless plug of my blog, which happens to be blog.jeremylickness.com. So I'm going to do that, and I'm going to click convert. I'm going to click convert. No, there we go. Ignore the delay. It was all in your mind. But there we have the Markdown rendered using a class library that was never even developed in the first place to run in the browser. The other thing I can do is I can go in the other direction. So if I come into my source code, I've got a class that is basically just a wrapper around the call to markdig, and I've tagged it as JS invocable. That tells Blazor that I want this method to be exposed so that JavaScript can call into my C# code. So then, to avoid a bunch of fumbling at the keyboard, I can come over here to the step-by-step demo instructions that you'll receive as well, and go into this. I'm going to come into the console, and I'm just going to paste this. And before I run it, what it's doing is it's saying .NET invoke method, that's provided by Blazor. Here's the name of the assembly, because we can have multiple libraries that we pull in. Here's the name of the method, and here's what I'm passing to it. And we'll go ahead and invoke that, and we get an alert that has the converted Markdown. Interesting? Intriguing? Intriguing. So, why WebAssembly? Speed. There's definitely a use case for the performance benefits it provides. Reach. It's accessible through all the modern browsers, including phone. That's accessibility. And diversity. It allows you to truly use the language you want to build web-based experiences. Now, we do have a couple extra minutes, so I just want to go into a bonus round, if you will. Let me see how quickly I can pull this one off.
I have a question about the accessibility thing.
Yes.
How well do screen readers like it?
So WebAssembly itself is not going to do anything as far as render any type of viewable element. It's going to process your code. So if I'm using Blazor, for example, I'm still using accessibility conventions that are HTML standard conventions for my tags, for my markup. WebAssembly is just doing... No, WebAssembly won't change the DOM. It's the JavaScript interop that changes the DOM. WebAssembly will only expose memory and return values. It cannot manipulate the DOM directly. Yep, so even when you saw like it doing the manipulations from Go, Go was actually creating a hook, so it was calling out into JavaScript. JavaScript was doing the render animation frame and then calling back in. So that's, and I use accessibility like it's accessible from devices. There's not a need to do any accessibility around WebAssembly itself because, again, it's like a black box that code comes in and out of. And then the accessibility is the layer of what you're actually rendering in the browser. So like, for example, for that chaos when I'm rendering the images, I would probably want to have some extensions and describe what the images are, or do something dynamically based on that, but that would be on the JavaScript side. Make sense? Yeah. All right, so let's do this. I'm going to just go ahead and run this. Because Go can target WebAssembly, I was into gaming in about 1977 timeframe. A virtual machine was created by a group of students at MIT who wanted to take an adventure game off a mainframe, bring it to personal computers. So we had Commodore 64, TI-99 4A, Altair, TRS-80, Apple. There were so many machines, different architectures, different languages. So they came up with the idea of let's build a virtual machine that runs games. We build it once for each platform, then we can write 200 games, and we just write the games to the virtual machine and not to 16 platforms. It was brilliant. They became a multi-million-dollar company. Then people got bored with text games, and it crashed. But someone basically reverse engineered that specification and came up with a Go interpreter about 7 years ago. So what I did was I said, let's see if we can target Go to WebAssembly. And it compiled without changes, just no change. But it was relying on standard in and standard out, so it wasn't very effective. So I just wrote a little bit of JavaScript code to intercept standard output and draw it on the screen. And then a little bit of code that took what I put in this text box and send it into the Go engine. And what I have here, if run actually works, watch this, we're going to see a a dead loop. Let's try it one more time. Let's go with Hitchhiker's Guide to the Galaxy. We'll try something different. This is actually doing a fetch, bringing it in, passing that buffer into the Go code, doing a run. And if this doesn't work, I'm aborting out. Okay, so you see that there was no verb in that sentence, so it's thinking it's getting input that it's not. So I've obviously done something wrong. But just imagine how cool it would have been if you would have seen a text-based adventure game that we can interact with. I've blogged about this online. You can see it actually working there. But I don't want to keep you from lunch any longer, so if you want to take a picture, this is a good slide to do it. I will tweet out the link to this deck. Every example I showed you is open source, and each one has step-by-step instructions to set it up and run through it. I will hang out a little bit afterwards in case anyone has additional questions. Thank you so much for spending your afternoon with me.